All right, let's get started. We're going to finish chapter 3. We're going to talk about how to name ions and ionic compounds. And then here's the goal. It's not a surprise. Obviously, this is not for a grade, so please engage with this as much as you can. When we finish the lecture material, I have some review questions. So what I'm going to ask you to do is to put away your notes, and I want you to test yourself, okay? What do you have to lose? Except for maybe to realize what you need to spend time studying, which is a great thing. A lot of times, we think we know the material or we know how to work something until we put everything away and try to do it. And then you realize, oh, I don't think I know that as well as I thought I did. So that's going to be the goal. We're going to spend I think we finished up with about 20 minutes to go in the first lecture. And we'll spend that last 20 minutes. I'm going to time it. So I'm going to say, time's up, let's move on. And then we'll go back and rework most of the stuff. And then whatever we don't get to, I have more reviewed material than we will possibly get through. So whatever we don't get through, I will share with you guys the slides, and you can work that stuff on your own. And if you have questions, if I need to post answers, I can do all that. So, okay, y'all ready? I'm ready. If you're ready, say I'm ready. All right, share my screen. Whoops. Okay. Here's this. Let me move some stuff around on my screen so I can see all your lovely faces, as many as I can. And the chat. I'm going to pull the chat up too. Chat. Okay. All right, here we go. So Tuesday, we talked about, we started to get into chapter 3, and we talked about what an ion is. And there's two kinds of ions, cations and anions. We talked about how you form those. And we also said there's another kind of bond. We talked about chemical bonds. That was the first thing we talked about. We said there's two kinds of bonds. There's ionic bonds, which is the chapter 3 stuff we've been going over, where an electron is completely traded from one atom to the other. Completely lost by one atom, completely gained by another, and that's what creates the ions, because you have a charge imbalance now. And then there's another kind of bond. Does anybody remember the name of the other kinds of bonds that we can form that we're not actually talking about for chapter 3? Covalent bonds. Thank you, guys. So covalent bonds, electrons are shared. All right, so I'm just going to make a little note of that. We have, ionic bonds. Okay, and here electrons are traded or lost and gained. And then covalent bonds and electrons here are shared. Now, somebody asked at the end of lecture, I don't remember if it was the AM or the PM group, they're like, what about group number 4? Because one of the things we talked about on Tuesday was that certain groups on the periodic table are very predictable. And if we understand the octet rule, we can predict what charge each element will have, okay, as an ion. However, we did not really talk about group 4 here, because how many valence electrons does group 4 have? They have 4, okay? So do they want to gain 4 to get the octet, or do they want to lose 4? Well, it's 6 one way, half a dozen the other. We don't really know, because they don't really give away or receive electrons. They are more so, carbon is you're not really gonna find it very often. I'm not gonna say never. You're not really gonna find it as a +4 cation or a -4 anion, okay? They participate in covalent bonds. So just know that, and you're really not gonna have a lot of group 4 elements on the exam for exam 1 either. Okay, so let's talk about how to write the names of cations. There's 2 different ways depending on what kind of cation you are. You can either be a main group cation or a transition metal cation. Remember, metals form cations, they don't form anions, all right? So if you're a main group cation, and you should remember how to count main groups, you invariably carry 1 charge. You name the element, and then you add the word ion, okay? Name the element, add the word ion, and that's what we can see here. Here we have a group 1 element, potassium. It's always a +1. All the elements in main group 1 are going to form +1 cations because they have one valence electron that they give away. That's how you become a cation. So we call it the potassium ion. Group 2, we have Mg2+. It's given away, magnesium has given away its 2 valence electrons. Same thing with calcium, same thing with anything in group 2. So we just name it the magnesium ion. Okay. Remember on Tuesday, we said there's times where you're going to use Roman numerals, but that's not for main group elements because Roman numerals are only necessary when you can form cations with different charges. And these elements, the main group elements, they always give away the same number of valence electrons and they form a cation with the same charge every time. All right, aluminum, group 3. We didn't talk about group 3 a whole lot, but the trend continues. They have 3 valence. When they give away all 3 of those, aluminum could gain 5 and have 8 in its outer shell. That's a lot of work. It's way easier to lose 3, okay? And its ionization energy isn't that high, so it's way easier for it to lose 3, and it's going to become a +3 cation, and so we just call it the aluminum ion. All right, transition metal cations. First off, there's 2 naming systems that you're probably looking at, noticing, and I don't want to talk about this one. We're not going to do the old naming system, okay? So cross that out. You might have been introduced to it in a previous chemistry class, and it still exists, but we're only going to use the new naming system. Okay, so let's talk about the new naming system. If you're a transition metal cation, you also name the element, and then you use Roman numerals to indicate the charge. Okay. The reason we do this, once again, as a reminder, is some transition metals, lots of transition metals, they'll lose their valence electrons. By the way, how many valence electrons do transition metals have? Anybody remember? 2. So they're going to lose 2, and sometimes transition metals only lose 1. Like we use silver as an example. It'll lose 1 electron. It just forms a +1 cation all the time. That's all it ever does. So, but they'll lose 2, and then sometimes they can lose additional electrons, and they can form multiple cations with unique charges, is what we said on Tuesday. And you see an example of that here with chromium, okay? So we're going to name the element. Then we use Roman numerals to indicate the charge. A +2 means 2 Roman numerals here. And then again, you add the word ion, okay? Add ion. Same idea. We have a chromium +3 as well. So chromium can lose 2 valence electrons, or it can also lose 2 valence plus 1 more, okay? And so we would put 3 for the Roman numeral to indicate the charge, right? Now, example with silver. Silver always does this. It just forms a +1. I would accept either thing. I would accept silver, Roman numeral 1. That's okay. You can omit it if you want, and you can just write the silver ion, or you can write silver 1 ion. I would accept both. All right. You don't have to go memorize which transition metals invariably form one kind of cation, just so that you can omit the Roman numerals. Just know that if you use Roman numerals on transition metals, you'll be counted right. Now, if you use Roman numerals up here on any of these main groups, I would count you wrong. If you told me the sodium 1 ion, okay, which sodium is a +1, but we don't need Roman numerals because it's always only ever +1. It'll never be a +2 or a +3. So I would count you wrong here, okay, because Roman numerals are only used for transition metals, all right? Questions on how to name cations? All right. Naming anions. So naming anions is pretty straightforward and simple. Your anions are your nonmetals. Where do we find these on the periodic table? Some of y'all are like, okay, which side? It is on the right side. Thank you, Brendan. Right side of the periodic table is our nonmetals, and these are our anions. So some examples that you see here with our halogens, you take the end of the element name, okay? Take the end, and you change it to IDE, okay? So we make it IDE. So for our halogens, they often all, or I think all of them end in INE, and you change it to IDE. So bromine, when it's an anion, becomes the bromide, and then you add the word ion, bromide ion. The chloride ion, iodide ion. Now, where it's slightly different, but still the same concept, is with oxygen and sulfur. They don't end in INE, but you still take the last part of their name. Actually, only the U are there. And you change it to IDE, oxide and sulfide. Okay. Questions on that? All right. And obviously, I think we mentioned this, but you always write the charge as a superscript. I think we mentioned that on Tuesday when you're writing the formula for or the symbol for the ion. All right, with polyatomics, I'm going to remind you once again, these will be on the exam. These are the 11 in the red boxes that you had to memorize. So make sure you know these. When I say memorize them, you need to know both the name and the formula, okay? Most of them are anions. We have 2 that are cations, ammonium and hydronium. But make sure you know those for exam 1. And then a reminder here, for hydrogen carbonate ion, I use the term bicarbonate. Okay, so I would encourage you to remember bicarbonate instead of hydrogen carbonate, because that's just what I use. And then especially in chapter 10, when we get into acids and bases, this is a big component in our blood buffer, and so I'll say bicarb a lot. So I want you to know what I mean when I say that. All right. Okay, so that's a little bit on how to name the ions. Now we're going to be putting ions together to form ionic compounds. So an ionic compound is a compound made up of ions. Generally, they form between a metal cation and a non-metal anion. Okay, a metal cation and a non-metal anion. It doesn't make sense to put 2 cations together. Why? They both carry positive charge. We know like charges repel. Doesn't make sense to put 2 anions together for the same reason. So you'll have a metal cation and a non-metal anion. Okay. So we're going to look at some examples first where the charges on the cation and the anion are of the same magnitude. Okay. And then we'll look at examples where the charges are not the same magnitude. Okay. The other thing you need to know about ionic compounds before we do that is that compounds are always charge neutral. Ionic compounds are always charge neutral, meaning the amount of positive charge you have from your cations has to balance the amount of negative charge we have from the anions, okay? And we can't change the charges on them, but we can change the ratios, how many cations and how many anions we need to get a charge neutral compound. So we're going to look at several examples of how we do that. Let's look at this first one. We have a potassium cation and a fluoride anion. And down here is their electron dot structure, so you can see their valence. Potassium just has that 1, and it's going to give that 1 valence to fluorine. And when fluorine accepts it, now it has a full octet. Potassium is also satisfied because underneath it has a full octet, but we don't write any dots in on this potassium cation, but we do write the full octet for the fluoride anion. All right. Now, if we're going to write the compound, potassium has a +1, fluoride has a -1. Okay, so +1 and -1, that adds up to 0. Okay, and that's what we mean when we say a charge neutral compound. Okay, it adds up to 0. They're charges. All right. Now, because we have a +1 and a -1, we only need 1 cation and 1 anion to accomplish that. All right. And again, you do not have to write a 1, right? You don't have to write it if it's a 1. We ignore that. So just be KF. All right. Let's look at an example with calcium and oxygen. Okay, you have a +2 cation, so calcium is main group 2. There's its 2 valence electrons down here. It's going to give both of those away And it just so happens that oxygen has 6 valence electrons, if you remember, it's in main group 6, and it wants to get 2 electrons. So they can all do this in one contract here. Calcium's very happy to give those 2 valence electrons to oxygen, and oxygen has room to accept both. And when it does, you get a cation with a +2 charge and an anion with a -2 charge. Now, because the magnitude of charge is the same here, how many cations and how many anions do we need? We just need one of each. So it's just CaO. +2 and -2 balance each other to be charge neutral. That adds up to 0. All right. But now let's look at what happens when the charges and the magnitude on those charges are not the same. Okay, let's look at what if we combine the opposite cation and anion from the previous slide. What if we have now a potassium cation right here and an oxygen anion? Potassium only has 1 valence electron to give away. But for oxygen to be satisfied, it needs to accept 2. It wants to have 8. And if it just accepts this 1 from potassium, that's great, but then oxygen only has 7. So what do we do for both things to be satisfied and be in a compound with one another? What can we do? Well, again, you cannot change the charges, but we can change the ratio of how many cations and anions we need. If we had 2 potassium cations, we had 2 of these, now each potassium can give away 1 valence electron, and oxygen can accept both, a single oxygen atom. So if we just have 2 potassiums and 1 oxygen, then we can make a compound with that. And you'll see that the charges balance out. We have a +1 and another +1 because we have 2 potassiums, and we have a single -2. And that balances. That's charge neutral. So how would we write this compound? K, and we use a subscript to indicate how many cations, and then O. Okay. All right, let's look at the opposite example. Now our cation has a higher charge, magnitude of charge, it's +2. And our anion, what if we form a compound between calcium and chlorine? Calcium is +2, chlorine is -1. You run into the same problem here where calcium is wanting to give away both of its valence electrons to be satisfied and stable, like a noble gas. But chlorine only wants to accept 1, a single chlorine atom. So what can we do? Well, we can change the number of cations or anions that we need. If we have another chlorine atom or chloride anion, if we have 2 of these, now calcium can give both away and each chlorine can accept 1 electron. Now everybody's satisfied. And what we end up with is a +2 and 2 -1 anions. And when we add up all of that charge across the board, that balances, and that is charge neutral. So how do we write this as a compound? Well, we just write all the cations and anions we have accounted for. We have calcium, just 1, and we have chlorine, we have 2 of those. CaCl2. Okay, questions so far on how we're writing these ionic compounds?
Just to be clear, you have the -1 on the chlorine because each of those chlorines took 1 of the electrons.
Correct. Each chlorine took 1 electron from calcium. Yep. So that means.
Go ahead. And then you just rewrite it CaCl2.
Correct.
Okay.
Correct. Now, there's what I call the switch trick to help you out with this, because sometimes it won't be very straightforward. Sometimes it's a little more complicated. So what happens? Hold on, let me respond to a comment. Okay, so this is called the switch trick, or whatever you want to call it. But basically, we can look at the charge on our cation or our anion, and that the number there tells us how many of the other kind of ion we need. So let's look at an example. We have phosphate PO4 with a -3 charge. If you know your polyatomics, you know this one. And we have magnesium, which is a main group 2. So it forms a cation with a +2 charge. The charge on this ion, the anion, is the same is the same as the number of the other ion. That's how many cations we need in our compound to be charge neutral. The number on the charge of our cation tells us how many anions we need, okay? That's how many anions we need in our compound. So you just look at the charges and then you switch those when you write the subscripts for your compound. Okay. So let's double check. Is this charge neutral? How do we know? Well, if we have 3 magnesiums, that's like saying we have this. Mg2 plus, Mg2 plus, Mg2 plus. How much positive charge is that total? Plus 6, right? Okay, phosphate, we have 2 of those. So we have -3 and -3 because each one has a -3. And that adds up to -6. +6 and -6, that balances as charge neutral. Okay. Somebody
How did we know we had 2 phosphates?
Well, we looked at the charge on our cation. It was a 2. And that tells us how many anions, and phosphate's the anion.
Okay.
Yep. Somebody asked me this morning, they said, will the switch trick ever fail you? And I had to think, I don't think it will. I think it works just about every time. So I think it's a safe thing to use. That's why I'm introducing it to you. So you're definitely, it's a lot easier than doing all the math. And I think you can trust it. Now, ionic compounds, we want them to be written in what we call a formula unit. What do I mean by that? It's the simplest ratio between, simplest whole number ratio. We know we can't write these subscripts. These have to be whole numbers, right? Dalton's atomic theory says we can't bind half of an atom with something else. So they have to be whole numbers. And we want the simplest ratio between our cations and our anions, all right? That's what a formula is. Simplest ratio between the cation and the anion to give us the smallest possible neutral unit. Okay, because here's the deal. You could have a neutral, a charge neutral unit even if you had this, Mg6PO4. Okay, let's check that. We know magnesium is up here, +2 cation. So if we have 6 of them, that means we're going to do 6 times +2 because each one is a +2 charge. We have 6. So that means we have a magnitude of +12 charge from our cation. Okay, what about the anion? If we have 4 phosphates, each one has a -3 charge. So we got 4 of them times -3. Each one's -3. So that gives us -12. So yeah, +12 and -12, that gives us a charge neutral unit. But look at these numbers, 6 and 4. You can simplify those numbers. They both divide by 2. So that's what we're saying. We want the simplest ratio. And here, 3 and 2, let me erase so you can see. 3 and 2 give us the simplest ratio. And the switch trick will always give you the simplest ratio, okay? I mean, double check yourself, but it should always give you the simplest ratio. Okay, so that's the switch trick. That's how you write formulas for ionic compounds. But we're gonna practice that some more as well. Here's 3 more rules you need to know when you write out formulas, okay, for ionic compounds. First, write the cation. Write cation first, anion second. Okay. For example, if we have a compound that has calcium and oxygen, calcium is a +2, oxygen is a -2. So when we go to write the compound, we just need 1 each. But I should write it CaO, not OCa. This is wrong. Secondly, do not include the charges on the ions. You do not need to write Ca2 plus O2 minus. Those are implicitly understood. Okay, you can figure that out for any ion. So that's not what we want to do. It's just, we just write the letters. Okay, lastly, use parentheses around the polyatomic ion. So if we have a polyatomic, for example, up here, we had phosphate was the anion, and phosphate is our polyatomic. So if we have, it says use parentheses around the polyatomic ion formula if it has a subscript. Meaning if you need more than one, you have to use parentheses. And that's exactly what you saw up here with magnesium phosphate. We needed 2 of them. We needed more than one. So let me show you another example with this. Let's say I have calcium. I'm going to keep calcium, and let's go up to the polyatomic chart. I'm going to pick an anion. Let's do hydroxide. It's OH minus. Here we are. So we have OH minus. All right, so we know calcium is 2 plus, and OH is a -1. We just saw that. If I'm going to write the formula here, how do I get these to balance to a charged neutral unit? Well, you can do the switch trick. I'll need 1 calcium and 2 hydroxides.
He must have burnt Monday.
Somebody maybe isn't muted. It's all right. Did I say something funny? I know I'm very funny. All right. So if you need more than 1 polyatomic, you're going to put parentheses around the whole thing. You're going to put a 2. So let's look at what happens if I don't put the parentheses. If I just write it like this, OH2. Why is that wrong? It looks like the 2 only applies to the hydrogen. This 2 means everything in there. We have 2 of that. I can't see what you are writing. I can't see are you writing anything? Okay, maybe that's what's funny, is y'all can't see what I'm writing. Let me stop sharing and reshare. Okay, now can you see what I've written? Pull the chat back up. Sorry, everyone, hold on. Are you writing anything? I can't see what you're writing. Okay, sorry. You can always unmute yourself and holler at me. Can y'all see what I'm writing now? Hold on.
I can.
Oh, hold on, pencil. Can y'all see what I'm writing now?
Yes.
I'm writing a lot of chemistry. I'm showing you how electrons move. All right. Okay, good deal. So that's why you have to use parentheses. All right. Let's do another example. What if we have aluminum and let's pick another, let's do sulfate. SO4 with a -2 charge. Okay, so aluminum is going to be a +3. How did I know that? It's in main group 3, which means it has 3 valence electrons. So when it achieves the octet, it will have lost all 3. So it's going to be +3. And then sulfate, we said, is SO4, and it's got a -2 charge. If we do the switch trick, how many of each do we need? We're going to need 3 sulfates and 2 aluminum. So we'll write 2 right here. And if I write this 3, now it looks like I have SO43, 43 oxygen. That's ridiculous, right? So that's not right. That's why you have to put the 3 outside. Now it means I have 3 sulfates, okay, bonded to 2 aluminum cations. And am I charge neutral? We can always double check. If I have 2 aluminums, each one is +3. That's 2 times +3. So that gives me +6. If I have 3 sulfates and each one is a -2, that's 3 times -2. That gives me -6. And +6 and -6 give us 0. Questions? So these are all the rules. All right. Okay, so I want to practice with this slide as well. We're going to just practice this a whole lot today because this is definitely going to be on the exam. I could either give you a formula and have you write the name of the compound, or I could give you the name of the compound and have you write the formula. All right, and that will for sure be on the exam. So let's look at these. Let's do the first one, sodium ion and a chloride ion. If it helps you, you can write out the ions. I want you to write the name, and we're going to write the formula. All right, so if we have Na, we know it's a +1, and Cl, it's a -1. To write the name of the compound, you're just going to drop the word ion. What you have is sodium. You just name the cation and you name the anion, sodium chloride. And that is the name of the compound. You just name the cation, name the anion. Now, what's the formula? The formula is the cation and the anion, and you lose the charges. You don't write the charges in. It's just Na, and we need one each, so we don't have to write the ones. It's just NaCl. Okay, so that was a simple one. What about this one, number 2? Iron, what does that 3 indicate? Roman numeral. What does that mean? That means our
Transition metal?
Thank you, Courtney. It is a transition metal, but it means the charge on our transition metal, that means it's a +3 charge. Thank you, Brandon. Yes, +3. All right, now what is sulfate? And here's why you have to have these memorized. It's SO4, and it's a -2. So there's our cation and anion. We know we write the cation first, anion second. We drop the word ion if we're going to name this, and we call it the iron. Now, do I include the Roman numerals when I name this one in the compound? Yes, if it's a transition metal, it can form multiple charges. We call it the iron. We call it iron 3 sulfate. All right, now let's write the formula of the compound. We've written the formula of the ions. Let's write the formula of the compound. You can apply the switch trick here if you want to. It should be Fe. It looks like I'm going to need 2 of those. And it looks like I'm going to need 3 sulfates. So I'm going to put parentheses SO4 with a 3. Am I charge neutral? I'm going to do 2 times +3. That gives me +6. And then I'll do 3 times -2. And that gives me -6. Oh, what did I just write? Gives me a loop-de-loop. Okay, -6. +6, -6. Those add up to 0. I am charge neutral. All right, sodium ion and bicarbonate ion. We know sodium is Na+, bicarb, HCO3 -1. Again, how did I know that? I've taught this class a few times. So how do we name the compound? How do we write the formula? Well, name, you just drop the word ion. So it's sodium bicarbonate. And we just have a +1 and a -1 here. So this one's simple, NaHCO3. Do I need parentheses around my polyatomic? HCO3 is a polyatomic. Do I need parentheses? Yes, no, maybe so. You only need parentheses if there's more than one. There's only one here. So just by writing it, you don't need parentheses. So if I did this and wrote 1, that's very redundant, right? We don't need to do that. Okay. Last one, ammonium. What is ammonium? It's not an element, that's a polyatomic. It is NH4, it's a polyatomic cation. Those are a rare breed. Okay, again, most of them are anions, but it's NH4+. What is phosphate? We looked at phosphate earlier with the switch trick example. It was PO4 with a -3 charge. Let's name it. Drop the word ion. You should have ammonium phosphate. And to write the formula, you do the switch trick. This is a +1. So that means I'm going to need 1 phosphate. And this is a -3. That means I'm going to need 3 ammoniums. Now, this is a polyatomic, don't forget. So we've not seen this yet. It doesn't matter that it's a cation. It's still a polyatomic, and we need more than one. We're going to have a subscript. So I cannot write this. Can't write that. I've got to use parentheses here. And then you only need 1 of your anion polyatomics. So this was a compound made of 2 polyatomic ions. We put parentheses and a subscript around the cation, and we only had 1 anion, so you did not need parentheses around PO4, even though it's polyatomic. Okay, questions? All right, I wrote a poll for this one. So we're gonna do a poll. You're gonna name these ions. I forgot in the 1050 and we like answered all of them. And then I showed them all this beautiful work I did last night. That was a total waste. Okay, so just name these ions. You have to do all 4 before I think you can submit your answer. You might want a periodic table if you're not super sure on which things are transition metals and which ones are main groups. And you probably noticed I wasn't able to use superscripts on the charges, sadly. Zoom needs to ask me what my feedback is for them. It's not very chemistry oriented. So normally you wouldn't want to write them the way I have them on this poll, but I had to indicate the charge somehow. We're almost there, 46 of 55. We're low today. You need to call your friends and tell them to attend class. Man, days like this, they make me want to like offer something for like points just because people aren't here. That's terrible. Dallas, I'm looking at the chat. Dallas, the due date is by exam 1. So by next Tuesday. There's a discussion board question. You can get 2 bonus points. If you've already done it, great. I will respond to you eventually. It might take me through next week and even the week after to get to respond to all those discussion board questions. So if you've given me feedback about how this class could be better, I want that. And if you haven't seen any change, it just maybe I haven't read your response just yet. Okay, I think I'm going to end the poll. I think we're as close as we're going to get because it's been 3 minutes. Let's look at the answers here. Most people voted for copper 2 ion. Y'all think that's correct? Cu2 plus. Is copper a transition metal? That's the question you have to ask yourself. Is it transition or main group?
Transition?
It is. It's a transition metal. So copper can form a +1 or a +2. So we have to use Roman numerals here. So the majority got it correct. It should be copper 2 Roman numerals ion. All right, next one. We had F with a -1 charge. That is fluorine. But when it's a -1, it's the fluoride ion. You don't need Roman numerals here because your anions you're never going to use Roman numerals on anions because you'll never have a transition metal that's an anion. So fluoride ion is correct here. Okay, number 3, the magnesium Mg with a 2+ charge. The majority voted for magnesium 2 ion. Is this correct? No. Why?
Because it's not a transition metal.
Thank you, Aubrey. It's a main group 2. We don't use Roman numerals on main groups because they never, magnesium, you'll only ever be a +2. That's all you'll ever be in life, right? Just a +2. So quit trying to be other things. You don't need Roman numerals there. Because it's a +2, you just write magnesium ion. So that first choice was correct. Name the following ion S with a -2 charge. This is sulfur, but as an anion, how do we name anions? We put the IDE. So it should be the sulfide ion, not the sulfur ion, not sulfate. Definitely not sulfite. So if you pick sulfate or sulfite, you need to go revisit your polyatomics. Okay. Sulfide ion is correct there. All right, that's the first poll. Let's continue. Now we're going to write the symbol for these ions. All right, so we have silver. Again, silver's 1. You can actually omit the Roman numerals, but you don't have to memorize that. So silver 1 ion. So you just write the name of the symbol for the element, and you write the charge as a superscript up top. There it is. Iron 2. So you just go find iron, which is right here, Fe. So it'd be Fe, and then this 2 Roman numerals indicates that it's a +2 cation. Calcium is where? It's right here. It's in main group 2. Means it has 2 valence electrons. It's going to give away both of those to get an octet. When it gives away 2 electrons, I'm just going to walk through this one a little more slowly. We start out with 20 protons, right? And 20 electrons. But when it gives away its 2 valence, now we have 18 electrons. We still have 20 protons. So +20 and -18, that adds up to what? +2. Okay. So there's the symbol for that ion. And oxide, oxygen is right here, main group 6. So that means we start out with 6 valence electrons. Okay. It wants to have an octet. So is it going to lose 6 or is it going to gain 2? It's going to gain 2. So if we start out with, I'm cramped, I'll zoom in. If we start out with, I think, 8. The atomic number for oxide is 8, so that's 8 protons. We started out with 8 electrons. We're going to gain 2. Now we have 10 electrons. +8 and -10 adds up to -2. So our symbol here is oxygen with a -2. Okay. Questions? Am I moving too fast? Are y'all keeping up with this? You doing okay? All right. This is actually the periodic table you have it available for the quiz today. That periodic table page in the quizzes folder is there. And then I'll also post a resources page. Can you go over the last one again? Yes, I can. Let me finish talking about the periodic table. We'll go back to that. This is the same periodic table you'll have for exam 1. And then I'll also remember, I'll give you the formula for temperature conversions from Fahrenheit to Celsius and Celsius to Fahrenheit. Okay, so you'll have that resources page in Blackboard. Does the charge go before the number or after? It doesn't matter. Okay, we have a question here. We have 2 questions. Let me answer Dakota's because that's simpler first. Dakota, you're asking, are these the same thing? And yes, these are the same thing. I could care less if it's -2 or 2-. That means the same thing. And same for cations, +2 or 2+, or +1 or plus, whatever, as long as both things are there. All right. But somebody wanted to go over the oxide again. So I'm going to actually, if we have oxygen and we want to know what's the symbol for the oxide ion. Oxygen, let's look at the periodic table. I see this 8 right here. What does that 8 mean? That's the atomic number. The atomic number tells us how many protons are in the atom. So what that means is that oxygen as an atom has 8 protons. Okay? Protons are positively charged. It also, as an atom, has 8 electrons. Oxygen 6 of those 8 electrons, they're valence, okay? So it has 6 valence electrons. 2 of them are not valence because they're on the inner shell. I could draw you a picture. Let me draw you a picture. There's the nucleus. There's the 2 electrons on the inner shell. And then here's 6 valence electrons. Okay, oxygen wants to have 8. So we're gonna, when it gets those 2 additional ones and becomes an anion, we still only have 8 protons, but we added 2 electrons, and now we have 10 electrons. Okay, and when you look at the ion now overall, you look at the total positive negative charge balance. You have a positive 8 and a negative 10, and that adds up to negative 2, and that's the charge on the ion overall. Does that help, Bailey? Hope it helps. Okay. Any other questions? Here's more practice problems. These are ones that you can totally practice on your own. It's just more of what we've been doing. I really would like to spend the last 20 minutes or so on this review stuff, but we have one more slide. We have reached the end, everyone. This is the last slide for the exam 1 stuff. Last thing you're going to learn from chapter 3 is properties of ionic solids. So ionic compounds, we don't call them molecules, we call them ionic compounds or crystalline solids. Those are the proper names. We call covalently bonded compounds, we call those molecules, okay? We'll talk about that after exam 1. Now, some ionic compounds dissolve in water to form solutions that are good conductors of electricity. Okay, why do they conduct electricity? Because you have ions in solution, and the ions are charged, and things that are charged can conduct electricity, okay? Now, this picture here that you see is kind of a cartoon picture of sodium chloride. So you have the sodium atom and the chlorine atom. Remember, when something becomes a cation, it gets smaller. So here it is as a cation, and it's smaller in size. When something becomes an anion, it gets bigger. So the chloride anion is bigger than the chlorine atom. The sodium cation is smaller than the sodium atom. Now look at this, this figure over here. You notice something that is very ordered. It's very arranged. Okay, that's because anything that's positive is going to surround itself with things that are negative. Okay, unless we're talking about our friends. But things that are negative are going to surround themselves with things that are positive. So because of that, you get something that's very arranged and very ordered. We're not going to put positive cations next to each other and negative anions next to each other. So that's why it looks very organized. Now, because of that, because you have all these ionic bonded interactions, okay, if we are looking at this sodium right here, it is bonded to that green sphere, that green sphere, that green sphere, that one, and then even more green spheres we can't see inside. And if we projected this crystal out towards us, there'd be even more. There's a lot. This sodium isn't just bonded to one anion. It's bonded to like 8, okay, as many as it can be. So because of that, ionic compounds have very high melting and boiling points. There's a lot of interactions that are holding these compounds together. So it takes a lot of heat or a lot of energy to break apart all those interactions and melt things and then evaporate or boil things. Lastly, they shatter. Because the ions are so orderly and arranged, when you break them, they break across a plane usually. It's kind of a nice clean break. So like if you break glass, you notice that it shatters. All right. Okay, that's properties of ionic solids. We're going to do one more poll to make sure you understand what we just talked about. So, poll number 2. Let's look at this question. The melting points for NaCl, KCl, and RbCl. These are all ionic compounds, are respectively 801 degrees Celsius, 770 degrees Celsius, and 718. So those are really high. Based on this, which compound exhibits the strongest ionic bonds and which one exhibits the weakest? All right, we're almost there. Go ahead and get your votes in. I'm going to end the poll. We've had a minute and a half. Okay, so the majority picked that the one with the highest melting point had the strongest ionic bonds. That's NaCl. The 801 degrees Celsius, that's NaCl's melting point, right? So because it has the highest melting point, that means it has the strongest bonds. It takes the most amount of heat or energy to break apart ions of sodium and chlorine. It takes less energy to break apart RbCl, rubidium chloride. That had the lowest melting point, so it melts the quickest. All right, so what you learned here is the stronger the ionic bond, the higher the melting point and the boiling point. Or I'll say it the other way. The higher the melting point and the boiling point, the stronger the ionic bond, and then vice versa. Okay? All right, are you guys ready to do a review? I'm ready. I'm going to time you. It's going to be a lot of fun. So here's the deal. The reason I'm doing this, again, you may be like, yes, I totally understand everything. If you had to take the exam tomorrow, okay, which you don't, but if you did, this is going to show you, where your strong points are, and then it's also going to reveal to you where your weak points are and what you maybe need to spend time studying. And that's the goal. I don't want you to spend time studying things you know well. I want you to spend time on the things you don't know well. Now, here's the deal. This is also not a comprehensive review. There are going to be things on the exam that we don't get to in the next 20 minutes, okay? But I'm going to try to cover several topics. You do your best. If you don't finish something in the amount of time that I give you and I scroll to the next slide, it's okay, because we're going to come back and we're going to answer it. So you'll have the answers by the time we get done. Don't freak out. I want to time it because I want you to feel a little bit of kind of what you're going to feel on test day. I think that's healthy and that's good practice. You don't have to time yourself when you study. But here we go. Not graded, so don't freak out. You have 2 minutes. I want you to predict or write down 9 topics or concepts from chapters 1 through 3 that you think will be on the exam. Think all the way back to chapter 1. We talked about matter. Chapter 2 was atoms in the periodic table. Chapter 3, ionic compounds. Okay, you're a minute in. Give you another minute. I don't care how specific or vague they are. I mean broad, not vague. "20 seconds. I really only love time announcements when I'm like exercising. 10 seconds left. You can do it. Okay, 5, 4, 3, 2, 1. All right, let's go to the next one. Classify matter. What is the difference between a heterogeneous mixture and a homogeneous mixture? Can you give me an example? Don't write me a book. Just in the simplest, most concise words you can. What's the difference? I'm going to give you about 20 or so more seconds, maybe 25. All right, you've had about 50 seconds. I think that's should be pretty doable to simply state the difference and give me an example. So let's move on. Classify each of the following as either a chemical or physical change, and I don't think we'll need to spend a lot of time here. Freezing a popsicle, roasting a marshmallow, bleaching or coloring your hair. You need to ask yourself, are you creating something new? Or is there a sign of a chemical change? All right, that should be good. Let's move on. Let's get into some math. How many microliters are in 1.78 kiloliters? So grab your calculator if you need to. Aubrey's running. And when you finish that one, you can go on to the second one as well. That's a scientific notation problem. So you got to remember the rules for that. Okay, it's been about a minute so far, just to know how much time you've spent on it. Keep working. Don't use your notes. Don't do it. Make your brain think. Okay, it's been about a minute and a half. I say here pretty soon we're going to move on. When it gets to 2 minutes, I'll move on. Again, don't worry if you don't finish it. We'll come back. 5, 4, 3, 2, 1. Here we go. Dr. Michael prescribes 300 milligrams a day of medicine to a patient, to a patent. Whoops. Each pill has 1.5 times 10 to the 5th micrograms of medicine. How many pills will the patient need for 7 days, for a whole week? You want to, if you're sick, you want to go to the pharmacy. You don't want to go every day. Let's pick them all up at once when we go. How many pills is that going to be? So when the clock hits 3:45, since we'll have 10 minutes left at that point, I'll call it and we'll go back to the front and answer this stuff. Last minute. All right, 3:45, here we go. Let's name 9 things. Somebody I think may be unmuted. I'm hearing a. Hopping around. I'm just going to start with chapter 1 and work my way to chapter 3. So we talked about physical and chemical changes. Y'all double check that you're muted for me. And with that, there was the 4 signs, right? 4 signs of a chemical change. Number 2, we talked about classifying matter as a pure substance, so an element or a compound, and then a mixture, heterogeneous or homogeneous. Know how to do that. 3, we talked about prefixes and conversions between prefixes. You need to know base units with that, are kind of wadded in with that. The base unit for distance is the meter. The base unit for volume is the liter. The base unit for mass is the gram. What else did we talk about? We talked about density, or temperature, sorry, temperature. We did conversions between Celsius, Fahrenheit, and Kelvin. We talked about density as well. Work density problems. We talked about specific heat. And the units for energy, joules or calories, and the relationship between joules and calories. You need to have that memorized as well. What else did we get into? Heat. Anybody else have something that I don't have just yet? What was the last thing we talked about? We got into ionic compounds. Oh, I haven't even gotten into atoms. We got into atomic structure. Okay, and the subatomic particles. So you need to know their mass in AMUs, their role in the atom, how things are organized, their charge. We talked about trends in or on the periodic table. All right. Trends in atomic radius, trends in ionization energy, trends in electron affinity. And then we also talked about valence electrons. Now, obviously, I haven't even touched chapter 3 today. Chapter 3 talked about ions, how to name ionic compounds, how to write ionic formulas for compounds. So that's just 9. If you had other ones, that's great as well. Those are just 9 that I thought of. Classifying matter, what's the difference? Most simply stated, a mixture has more than one thing, more than one element. It could be a mixture of elements or a mixture of compounds, okay? It could be elements and compounds. But it has multiple elements or compounds. All right, that's a mixture. The difference between heterogeneous and homogeneous, I'm going to label this as 1 and this is 2. So number 1, a heterogeneous mixture is not evenly dispersed. The elements or the compounds are not evenly dispersed. Okay. The example I love to give is vanilla ice cream. You throw a whole bunch of, anybody ever go eat at like a Western Sizzlin in their ice cream bar, and you put in the M&Ms and you put in Oreos, and some weird people put in, okay? But then you grew up and you learned that gummy bears and ice cream are gross, okay? They're not evenly dispersed, right? Number 2, a homogeneous mixture. The example there is like sweet tea, all right? The sugar and the water, those are two different molecules, so that's a mixture, but it's evenly dispersed, okay? So the compounds, I'm just gonna say evenly dispersed, or mixed evenly throughout, even throughout. That's the main difference. And I know these words are very like simple non-chemistry words, and that's okay. I think you still get the concept. So we gave examples as well. Sweet tea and then ice cream with stuff in it. Classify each of the following as either chemical or physical. So there's key words here that indicate what each change is. Freezing. This is a change of state from liquid to solid. So this is just a physical change. Roasting indicates fire is involved. Any type of fire, combustion, explosion, roasting, toasting. This is a chemical change. Your marshmallow is not the same color when you get done roasting it. Bleaching or coloring your hair. This is a color change, right? Now, obviously, your hair is still going to be intact, hopefully, if you don't do a bad job on it. But you've changed the color. All right, so this is a chemical change. Bleach reacts with stuff. Bleach is a chemical. All right. Questions there. Remember that things that are diluted and things that dissolve, those are physical changes as well, not chemical. That was on the discussion board. Okay. Ooh, we only have a couple minutes left. How many microliters are in 1.78 kiloliters? So here's the relationships you need for this. And I know I'm going to move kind of quick, but this is recorded. You can go back and watch it. So 10 to the 6th microliters are in 1 liter. 1,000 liters are in 1 kiloliter. I'm going to use these. You probably may have written them out different ways. That's okay. There's so many different ways to write them. I'm going to start with the number given, 1.78 AL. I'm going to cancel kiloliters. Now I'm going to use this relationship. For every 1 liter, we get 10 to the 6th microliters. Okay, so you should have 1.78 times 10 to the 9 microliters. Liters cancel, kiloliters cancel. Questions there? Okay, let's move on to the next one. Scientific notation, when you multiply two numbers here, we're going to multiply the base numbers. Somebody tell me what they got. I think from this morning it was like 15 point, was it 0.1? Is that good enough? I'm sure there's more decimals. Now we're going to add the exponents. 11 plus -3. What does that give you? That gives you 8. So times 10 to the 8. But hold up, we don't have a number between 1 and 10, do we? So we got to adjust it. We got to take this decimal and bump it one more place to the left. Remember, when the decimal moves to the left, the exponent increases. So we get 1.51 times 10 to the 9. How many of you would I have got with a multiple choice question on the exam with this? Okay, remember that. Questions there? Okay, I know, again, I'm moving real quick. So holler at me if something's just not registering. All right. I can't see what you wrote. Again, did it disconnect me? Okay, we'll stop share. I've got a few minutes left. I've got 2 minutes. And that should be plenty of time to do this last problem. Okay, last problem here. Dr. Michael prescribes 300 milligrams a day of medication. Did that help? Can y'all see it now? Better? Okay.
Yes.
Good deal. 300 milligrams a day. So that's one relationship. I'm just pointing out relationships here. 300 milligrams a day. Each pill, so one pill has 1.5 times 10 to the 5th micrograms. I've noticed something here. I've got micrograms and milligrams. I'm going to have to convert between those two. So I have 2 different units of mass. Here's my question. How many pills? So I want an answer with unit of pills. So there's different places you can start. All right. You can start with the first relationship given if you want and hope that your units work out. I'm going to start with the second one. Each pill has 1.5 times 10 to the 5th micrograms because I know I want pills on top. So for every 1 pill, It's 1.5 times 10 to the 5th micrograms. If you started it different, that's okay. We probably will reach the same end, hopefully. Now I need to convert from micrograms to milligrams, okay? Because I have two different units of mass. So what's the relationship there? Well, I know that 10 to the 6th micrograms is in a gram. I know that 1,000 milligrams is in a gram. So I know these two things are also equal, right? So I can say 10 to the 6th micrograms is equal to 1,000 milligrams. That's perfectly valid, right? Because they both equal 1 gram, so they're both equal. So I'm going to cancel micrograms. I'm going to write it on top, 10 to the 6th micrograms. Now micrograms cancel for every 1,000 milligrams. Now I know that the doctor prescribed 300 milligrams per day. That's another relationship, 300 milligrams in 1 day. That's how much the patient needs to take. I'm going to cancel milligrams because I don't want units of milligrams in my answer. So per 1 day. And I know that we're supposed to go for 7 days. So milligrams cancel, days cancel, I'm left with pills. So how many pills did you pick up from the pharmacy? You patent, you? Anybody get it? You do 1, you cannot ignore this 1. Remember when you have a 1 in the first thing, 1 over this number is a different number than just 1.5 times 10 to the 5th. So you do 1 divided by that, times 1,000,000 divided by 1,000, times 300, times 7. What you get? We're a minute over. Did you get 14? That's what they got this morning. 14 pills, 2 a day. It's not bad. Some of us, our grandparents, take like 10 a day. We're all going to be there one day. Okay, any questions? I know, again, this moved fast, but it's all recorded for you. I'll put it all on Blackboard if you want to go back and watch anything, ask me any questions. Look at this. I have more review slides, okay, stuff we did not get to. Here's a huge, look at that, challenge problem. I'll share the stuff with you. Feel free to work through it over the weekend as you want. I'm not promising that I'm posting, like, I have a lot of stuff to do and I got to write the exam, so I may not, but if you have a question, like if somebody wants to know this challenge problem, I'm happy to provide the answer. Just shoot me an email. Do we have to submit our work on the exam like we did on the dry labs? There'll be a few questions where you have to take a picture and upload it. And I will say, I'm going to harp on this in an email. It needs to be in PDF format. It is such a hassle to me when it's other formats, okay? So you can always upload a picture on your phone to your Notes app. Somebody was saying this morning. Your Notes app. Everybody has Notes app. Now, you shouldn't be using your phone except to take pictures of your work. You can upload it to the Notes app. You can save it as a PDF in your Notes app or export it or whatever. I promise somebody said this was possible. They said this is how they did it. And you can upload it that way. Please upload your images as a PDF, okay? It is really, really difficult. Sometimes when I click on your picture, it like downloads to my computer and then I got to go search for it and blah, blah, blah. So anyways, here's extra slides. I'll send all this stuff to you guys. And thanks for joining us today. Y'all have a good afternoon. We have a Q&A tomorrow at 1:30, and I'll stick around for a few more minutes today if we have questions this afternoon.
I have a question.
Aubrey.
Okay, so on the chapter 3 homework,
Yes.
I finished most except 10 and 26.
Okay.
I did not know how, like, I do not know.
Okay, 10 and 26. Here, why don't I pull that up? We can look at it.
Yes, please, because my friend Hannah is also in the class, and I asked her if she knew how to do it, so maybe we could help each other. No, she doesn't know how to do it either.
Okay, well, I'll look at that real quick. By the way, the homework, everyone, is due Monday. So 10 and 26. So I'm going to
Right.
Mastering Chemistry right now. Mastering Chemistry. Chapter 3 assignment is what we want. Sorry, it's thinking for a second. Okay, here's our chapter 3 assignment. And is it like, you said 10 and 26. Is that right, Aubrey?
Yes, 10 and 26, I'm pretty sure.
Okay, now here's the deal. Sometimes it numbers them too two ways. So let me see if this sounds familiar. I'm going to click on one that says 10. This problem, let me see, standard view. Let me share my screen, and then let's see if this is the one that you're talking about.
Yes, that one.
So this one says blood serum in healthy adults normally contains approximately 3.2 milligram per milliliter of sodium ions and approximately 3.5 milligram per milliliter of chloride. How many milliliters of blood serum would be needed to obtain 1.9 grams of sodium ions? Second question, how many milliliters would be needed to obtain 1.9 grams of chloride ions? So this is just a conversion problem. So I've got it on my screen now. If anybody wants to screenshot the screen so you have the problem, do it now because I'm about to share to my iPad. And let's look at this. Need to get a blank slide. Let me pull up a blank slide. Okay, so I've got a blank slide, so I'm going to stop sharing on my desktop and I'm going to share back to my iPad and we'll look at this. Okay, let me just get this over. So we've got, and your numbers may be different on your account, but what the problem tells me is that we've got 3.2 milligram per milliliter, and that's milligrams of Na plus. Okay, so we're going to work the first problem. It says how many milliliters of blood serum would be needed to obtain 1.9 grams of sodium. So this is the relationship the problem gives us right here. It says we want 1.9 grams of Na plus, and we want to know how many milliliters of blood. So we're simply going to use this as a conversion factor to convert to mils of blood. Now, this is in grams. The number that they give us is in grams. So we first, to use this, we need to convert to milligrams. You see that? So right now we have grams of sodium. Let's convert to milligrams of sodium. So how do we go from grams to milligrams? Because we want grams to cancel, right?
There's 1,000 milligrams in 1 gram.
Perfect. All right, so grams will cancel. And now we can use this relationship. Okay, so now for every 3.2 milligrams of sodium, we're going to get 1 ml of blood. So grams of sodium cancels, milligrams of sodium cancels, and we'll be left with milliliters. Does that help?
Hang on.
Is it 59.375?
Okay, I'm getting some awful sounds here.
My bad. This helps, by the way. Yes.
So you're going to approach the second part the same way, but you'll just do it with the relationship for the chloride. The relationship there is 3.5 milligrams of Cl minus for every milliliter of blood. Okay, so the second problem tells you again, you want 1.9 grams of Cl minus. Okay, so before you can use this relationship, you've got to go from grams to milligrams of chloride. So you're going to do the same thing, grams to milligrams. You'll fill in the numbers. Once you have milligrams and grams are canceled, now you'll plug this relationship in. For every 3.5 milligrams of Cl minus, you get 1 ml of blood, and you'll calculate milliliters that way. Okay, what was the other problem you said?
26.
26. Oh, here it is. Okay, let me see if this is the right one so that everybody can see it. Oh. I'm gonna put the chat away. How do I do that? How do I like X out of the chat? Oh, close. Okay. Share to my desktop. Share. Okay, is this the other problem? An astringent. A compound that causes proteins in blood, sweat, and other bodily fluids to coagulate. Oh, this is taking me back to research days. So we did protein research, and that was the worst words in the world, that your protein coagulated. To coagulate a property put to use in antiperspirants. So an astringent is a compound that causes proteins in blood, sweat, and other bodily fluids to coagulate. And that's, they put that in. So deodorants, for example. We would put this compound in deodorants. Two safe and effective astringents are the ionic compounds, aluminum with sulfate ion and acetate ion. So you'll oftentimes, if you go like people that are very health conscious and tend to be mostly organic, they'll buy deodorants without aluminum, okay, because we don't really want metals absorbing in our body, right? It says write the formulas of both. Express your answers as a chemical formula separated by commas. So essentially we have, I'm going to share back to take a screenshot if you need to. All right. So we have, where did the problem go? Here it is. We have aluminum with sulfate and aluminum with acetate. So aluminum, can anyone tell me, if this is an ionic compound, what the cation is going to be and what the anion is going to be? We're going to write two compounds here. We're going to write aluminum with sulfate. We're going to write aluminum with acetate. For the first one, aluminum and sulfate. Which one's the cation? Which one's the anion? Which one's going to be positively charged? Which one's going to be negatively charged? Anyone? Well, if you know your polyatomics, you know sulfate's negatively charged. What will aluminum carry as a cation?
2, 3.
Yep. So now let's apply the switch trick. Remember, this is a polyatomic. What do you do when you have more than one?
Parentheses.
Parentheses.
Yes, thank you, Dakota. AL. So it looks like we'll need two of those. I think I did this example in lecture. I worked out a homework problem for you. You're welcome. Now you got to go find the acetate ion. That should be on your polyatomic chart. Acetate or acetic acid is what's in vinegar. So it's C2H3O2 minus, sometimes you'll see it as C2H3, or sometimes you'll see it like this. CH3COO minus, either way, it's the same thing, same number of carbons and hydrogens and oxygens. But aluminum is still our cation. So you do the switch trick here. If you need parentheses because you have a polyatomic, make sure you write those in. Double check that you're charge neutral. Okay, for example, with this first one over here, we have 2 aluminums. Each one is a +3, so I'll do 2 times +3. We have 3 sulfates, and each one is a -2. So that gave me -6. So yep, I'm charge neutral. Just make sure that on your second compound. Questions? Does that help?
So it'll be AL parentheses. No, wait.
So you
AL.
write your cation first, Al. Now you got to write your anion. Acetate is your anion.
Do you want us to write it exactly how it is on the table? Because it has CH3CO2.
Is it C2H3O2?
Yeah, CH3CO2.
Oh, okay. You know, that's a great question. I was actually wondering, mastering should not count off if you have the correct formula. So if you put it in as one of these ways or how it is, Hannah, on the table, and it counts off, please let me know, because it shouldn't. There's different ways to write acetate.
So it'd be AL2 parentheses CH3CO parentheses 3.
You said Al2.
Yes.
Do you need 2 aluminums? What's the switch trick here? This is a -1. Oh. We needed 2 the first time around. Why? Because the charge on our anion was a -2. But Morgan, what are you drinking over there? Oh, Starbucks.
The Starbucks, yeah. I just needed some energy to push myself to studying. It's like the vanilla frappuccinos. I love them.
Yeah, they're good. I have not had my iced coffee today.
Yes, I'm just doing a little late, but I have kickball later tonight, so I need to get energized for that too.
Oh,
Yeah, I'm doing part of the intramural teams. It's a lot of fun.
yeah, I saw that they're doing some intramurals.
Yeah, good exercise and like it's like all social distance, so it's nice, still seeing people, but like being safe.
Hannah wishes there was intramural lacrosse, right?
I wish we had intramural lacrosse. That'd be fun.
Wait,
Don't have the time to start that myself.
you're from Maryland, right? You're the one that's from Maryland? There's most of it. Okay, that's right. And your boyfriend plays lacrosse. Okay. So anyways, I know I didn't write it all out, but it would be Al, and then you'd write the formula for your acetate here, and you are going to need a parentheses 3 around that. Okay, guys. Well, I got to go. Thanks for joining today. Y'all have a great Thursday and Friday.
Thank you for helping so much.
Welcome. Very welcome. All right. See y'all.
Before you go, do we need Respondus for the exam? I want to make sure so I can have everything downloaded.
Nope, you don't.
Okay. All right. Thank you.
Welcome.
All right. See ya.
All right. Bye.